So what I want to talk about today is basically an introduction to deep learning, right? Crash course and what that means, right? So I think everyone has heard the term, but I want to say a little bit about what distinguishes what we talked about last time, multi-layer perceptrons, from what people talk about when they talk about deep learning, okay? And so, again, we have a whole course here in our department on deep learning. So the goal here is not to replace that course, but to maybe whet your appetite for taking this course, right? So, what's the difference between perceptrons and multi-layer perceptrons like we talked about last time and what people talk about when they say deep learning, right? So kind of one difference is, many neurons per layer, hundreds of neurons per layer, I would say. Many layers, dozens or more. And kind of special architectures, I would say. Ways of arranging the neurons and their connections. And so we're going to kind of talk about these, today, but there really is no official agreed upon description for when is a network deep and when is it shallow, right? So kind of what characterizes it is, more than one or two hidden layers. The layers are connected in some special ways, but there's no arbiter that says this is deep and this is not, right? So let me just talk a little bit about history for the first couple of minutes here. So kind of history is that 1958 was the perceptron, right? That's what we talked about a couple lectures ago. And as we showed, the perceptron was able to do classification of two classes that were linearly separable, right? And so, binary classification, this was the first algorithm that, well, not the first, but this was an algorithm that really worked, right? A lot of buzz, but it was claimed that basically there was no good way to train a multi-layer perceptron network, right? So kind of this is kind of like when the perceptron was proposed, let's say 69, there was a claim that no good algorithm for MLP training existed, which as we know is not really true, but that kind of put some cold water on the idea of using these multi-layer perceptrons for some time, right? Then in 1986, backpropagation showed how this training could work and how it could work in an efficient way. This backpropagation algorithm we talked about last time actually had appeared prior to 1986, as often happens, but people didn't quite recognize it for what it was at the time. So who gets credit for it and so on is kind of a subject of some debate. So 1989 was, something called LeNet, right? So LeCun, Jan LeCun from Meta, right? So basically, this was a CNN, convolutional neural network. We'll talk about what that means today's lecture. But basically, this could recognize, things like zip codes and so on, right? So, so the idea was to automate things like processing checks, processing handwritten letters, and this CNN had very high accuracy, right? So suddenly, people started to take a look at neural networks again a little bit, but it was still, tough to train these things in general because of the computational demands of training, right? And it also seemed like other algorithms still worked better at the time or worked as well. So again, if you read the history of, Jan LeCun and his rise to fame, part of that story is that for many years, he and other people who were doing neural networks were kind of laboring in the wilderness, people thought that they were doing this kind of niche activity, and then things started to kind of pick up, right? So basically in the 90s to the 2000s, I would say, continued neural network improvement, right? So basically, these are the people that you read about, Jeff Hinton, who just won the Nobel Prize, and Bengio, and all the kind of people who they say are the ancestors or the forefathers of neural networks, were working kind of in semi-obscurity from the 90s to the 2000s. Things became better and better as GPUs became commodity units that we as researchers could buy and use in our labs, right? Gaming was taking off, and so you suddenly had these GPUs that you could program to do general purpose operations. It was still kind of viewed as a, side approach, right? The thing that changed everything was in 2012, which was basically there was a paper called AlexNet. So AlexNet, which was used, we talked earlier about ImageNet. So ImageNet, a big part of it was this annual challenge of multi-class image classification. And so 2012, this AlexNet paper came out, which was also a convolutional neural network that totally blew away the state of the art by a wide margin, right? And then that made people wake up and say, wait a second, if we can go from getting 0.5%, 0.7% increases over the state of the art to suddenly being 10, 20, 30% over the state of the art, well, now maybe we should be paying attention to neural networks. And again, that was kind of like the perfect storm of the availability of massive data sets like ImageNet, GPUs for general purpose computing, and this kind of idea of the leaderboards of making sure you kind of knew where you stood with respect to other people on the same data set. And at that point, there was really no going back. Basically, everything became, neural network kind of was the first thing that you would try to solve any problem. And of course, these days, tools like PyTorch and Keras and TensorFlow and so on make it so easy to try neural networks and just set one up and run it that it's really commoditized so that the average person can train a neural network without really even understanding what's under the hood, right? So let me talk a little bit about what this convolutional neural network is, because to me, I think that's one of the things that distinguishes typically a deep learning pipeline from a just kind of regular, pipeline. So CNNs stands for convolutional neural net. Okay. And so kind of just a refresher is that last time we introduced this idea of MLP, right? So last time we talked about multi-layer perceptron, where the idea was that, and this is a very simple example, but the idea was that every input node was connected to everything else, right? So basically, if I'm trying to predict a number or do some regression or something like that, I make a network where everything is fully connected. So this is also known as a fully connected network. Or if I have something that goes from this to this, you would call that a fully connected layer, okay? So people began to be really interested in applying neural networks to images, right? And I'm an image processing guy, so I definitely saw this kind of take over firsthand in my field, right? So if I think about what is an image is a collection of pixels, right? So let's suppose that I have a 100 by 100 image. So if I were to kind of label the pixels 1, 2, 3, ... So then this pixel would be 101, 102, ... And then this pixel over here would be pixel number 10,000, right? So if I was going to make an MLP that processed the pixels of this image, you can imagine that it would have 10,000 by some number of connections going into that first layer. There's all of a sudden a huge number of parameters that you have to train, right? Which is, not out of the question for modern GPUs, for sure. I mean, the networks are very large. But one thing that's kind of important is that, if I think about how these neurons are connected, that, this neuron here, number 1, in a way, as an image processor, I feel like this neuron and this neuron should be related because they're close together, right? So for example, if I look at, these guys, I feel like there should be a closer relationship between these 3 neurons than between, say, neuron number 1 and neuron 10,000, or neuron number 1 and neuron number 587, right? There has to be some sort of idea of spatial adjacency between inputs that is not captured by the idea where everything is just connected together, right? So this is, kind of like the key idea behind CNNs is especially if processing images, we want the network to have an idea of kind of adjacency. And so this is strongly related to the idea of digital signal filtering or image filtering, right? So I know that many of you are comp sci people, but maybe you didn't take signals and systems. I don't know what to deal with this little blurb that this guy is doing, but what can I say? I don't know why this thing is like constantly screwing around here. All right, hey, projector. Quit your goofing around. Yeah, I don't know. All right, well, sorry about that. So the key relationship is to filtering. So just show of hands, who took like signals systems? Yeah, not bad, right? Not everyone, but not bad. So you may remember from a class like that, if you took it, that there was this idea called convolution, right? A much hated, concept in the first 2 weeks of signals systems, right? No one likes convolution, right? But the idea was that you had a signal, and you had what was called a filter, which was normally a little set of numbers that was, shorter than your whole signal, and you would take this filter and you would run it across the signal, and at each point, to produce an output, you kind of look at which of these things overlap. You add these numbers and you multiply corresponding numbers and sum them up, and you get some new value here. And so, for example, if I wanted to do signal smoothing, what I might do is use what's called a low-pass filter. A low-pass filter for smoothing might look like, a tray of numbers that looks like this, that says, okay, I'm going to center this set of numbers over my input, and I'm going to do nothing more than just average me and the two neighbors on either side, right? And so that's a way of taking a signal that has a lot of spikes in it and smoothing it out to be a little bit less spiky, right? So low-pass filter is a very common thing, right? The same thing applies in the image processing world, right? So for image processing, if I have an image, I can make a two-dimensional filter by, for example, taking a little tray, like a little 3x3 set of numbers, like this, for example. Bless you. Right? So again, what I do is I take this little 3x3 tray of numbers and I run it across the entire image, and I compute the response to the filter by adding up corresponding values, right? And so what is the effect of this filter? Well, the idea is that suppose that I had an image like this. Okay. Well, if I put this filter, if I center it, over here, where all these numbers are basically constant, then, if all the numbers are the same, then this plus 2 is going to cancel out with this minus 2, and I multiply the two numbers together, and so on. So basically, the response here is going to be, 0. And the response here is going to be 0. If I put that filter kind of like somewhere over a, vertical line, then again, since the numbers above and below are always the same, that means that, again, I'm not going to get any response here. But the interesting thing is, what happens if I put the filter kind of centered over here? Well, what happens is that there's, a big value, like white is 255 in the digital image world, and black is 0, right? So it's like saying that, well, here I'm going to have a bunch of 255s minus a bunch of zeros, and the filter response will be high, right? So this is an example of an edge detecting filter that is sensitive to horizontal edges, right? And you can imagine if I tilted this filter 90 degrees, I'd have a filter that responds to vertical edges. And if I tilted it so that the 2's and minus 2's were in the corners, I could get something that was sensitive to 45-degree filters. And if I made a bigger filter, then maybe I could make something that was sensitive to even more fine angles, right? And so if you took a class like digital image processing, which is something that I've taught a bunch of times, and I think we're offering it again in the spring, you'll learn all about these digital filters, right? And so the one thing I didn't mention when I said convolution, right? So convolution, there's a little bit of extra step where you are flipping the filter around before you drag it across the image, right? For our purposes, that flipping part is not super important for what we're talking about for neural networks, right? And everything I talked about here is basically symmetric anyway, so the flipping is not going to make a big difference, okay? So let's go back for a second and say that the philosophy in some sense behind neural networks is, we originally started talking about regression and classification using this phi function, right? The phi function was something that was like a mapping of the raw input to some features, and you as the user had to choose what you thought a good mapping might be. Maybe a polynomial basis, maybe a radial basis function basis like we talked about in homework 3. But the idea of neural networks is that we don't have to be so careful as users to figure out what a good basis function might be. We let the neural network itself decide how to combine the features in these nonlinear ways, okay? In the same way, even though I could hard code some information into my network to say, okay, I want my network to detect horizontal edges and vertical edges, right? I could hard code these weights into my network, but in practice what I do instead is I ask the network to learn a bunch of filters like this that seem useful for the regression or the classification task. So in some sense, what a convolutional neural network is doing is it's learning good filters, and then hopefully those filters correspond to things that make sense to humans, but they may or may not, right? And so the critical thing we're going to take from this idea is that, to produce the output from the input, I'm only acting on a small number of adjacent pixels or adjacent numbers, right? So if I want to figure out the output here in the middle, I'm only going to use 9 numbers in the image that are right in the middle. I'm not going to use all 10,000 numbers, right? Which means I don't need a fully connected network to accomplish that kind of computation. What I need is a network that is sparse, right? Meaning that there are very few connections between layers, right? Corresponding to basically the size of my little filter. And number 2, the idea is that the connections will be shared, right? That is, when I look at this set of numbers, I'm applying the same set of numbers no matter where I'm putting that tile over the image, right? So I'm really only using these 9 numbers to produce the output. I'm not using, 9 times the number of pixels because I'm sharing the coefficients, right? So let me write that down. So, idea behind a convolutional layer in a network is that, number 1, the connections are sparse, right? Only a neighborhood of local inputs is going to be what makes the difference for the output. And number 2 is that the weights are shared. So let me just do a toy example, right? So suppose that I've got a 3x3 image, okay? Label these pixels from 1 to 9. And let's suppose I have a 2x2 filter with these weights. What would the corresponding layer of a neural network look like, right? So I basically would have 9 input nodes. And if I think about filtering this image, there's really only 4 places that this tile can go. So when it's centered over here, then the connection between, I'm connected basically to 1, 2, 4, and 5. And the weights on those connections are A, B, C, and D, right? Then I can have a guy over here where I'm connected to 2, 3, 5, and 6. Then I've got one that's connected to 4, 5, 7, and 8, and one that's connected to 5, 6, 8, and 9. And again, these are shared numbers, right? So here, like, the connection here has weight of A from 5 to this node, right? A, B, C, D, right? So the idea is that there are only 4 unique weights. Even though it looks like there's lots of lines between the layers, I'm only learning 4 numbers, right? So that's the cool thing, right? Is that there is a lot less to store. There's a lot less computational overhead to train. Orders of magnitude less connections and numbers in a convolutional layer versus a fully connected layer. And the nice thing is that this is also independent of the input image size, right? Because I'm only learning the 4 numbers. I'm not learning like anything other than A, B, C, D, okay? So that's the cool thing. That's the main concept of a convolutional layer, is that I'm taking a single set of numbers and I'm learning that for the entire, basically 2x2 image. Now this really only makes sense when your inputs are like images or 3D objects or something like that. But that's okay, because so much of machine learning is applied to images anyway, right? So like computer vision, I think, was really the first like use case of these kinds of machine learning algorithms, right? And many of you in your projects, I'm sure, want to use images, right? So it's natural for you to think about convolutional layers for that, right? Another thing that is nice in some sense is that last time we talked about how can I make my network more robust to differences of the input that I didn't train on, right? So for example, we were talking about this idea of if I'm trying to recognize a 6, I want to be able to recognize that 6 no matter where it is in the image. Well, this kind of convolutional network has that idea built into it, right? The translation invariance of things is kind of baked into the network because I'm using the same set of A, B, C, D no matter where I am in the image, right? So another advantage is kind of, some automatic translation invariance. And so just like we would tune the weights of a normal neural network, here we're going to tune the weights of the filters that we want to apply, right? And so in practice, what happens is that we're not actually just going to learn the filters, the coefficients for one filter. At every layer, we may say, okay, I want to learn like 20 or 50 or 12 filters at this layer. And so typically what happens is that, so typically we don't just learn the weights or the, the weights for one filter. We simultaneously learn or maybe apply a bunch of filters at once. At each layer. And these are called channels or feature maps. So I'll show you in a second. I didn't prepare one, but I'm sure I can just Google one. So basically, when you look at a explanation of a neural network architecture, what you may see is basically a block that looks like this. That's kind of like input comes in, output comes out. And what you see here is kind of like a, m by n by k little rectangle. And what this means is that we are learning, k m by n filters. And actually, just let me see if I can Google something while we're talking here. I'm just trying to pull up a good picture. Right, so if I kind of look at, something like this, right? This is like your typical picture of what a neural network thing looks like. Why can't I see this in? I don't want to report it, I just want to see it. Yeah. What is it? I don't know. Right. So here, for example, you basically see, like here instead of a cube, it's drawing it like a whole bunch of pages, right? But the 24 by 24 means that I'm learning a 24 by 24 sized little filter, and that there are n1 of them, right? And so this is a very typical thing. And at the end, maybe I have I don't want to learn for free. At the end, I have a fully connected layer where after I've done my convolutions, maybe I add some fully connected layers, right? So part of network architecture design is figuring out, kind of the right way to arrange these layers. And so that's kind of like the fundamental idea. Now, there are many little nuances to making this work. So let me stop and ask questions about the basic idea. Okay, so one thing to keep in mind is there's also something called the stride. So there are other choices to make. One thing is called what's the stride, which is basically talking about, how do the fancy word receptive fields of the neurons overlap, right? So for example, let's say that I have, this is just the same image 3 times. And let me just draw some dots here to indicate pixels or whatever. So the idea is that when I run this filter across the image, normally if I'm doing like typical image filtering, I place the filter over here, and then I click it over 1 notch, and I place it here, and I click it over 1 notch, and then when I'm going down this row, I click it over 1 notch. This would be like stride of 1. Or I could click it over 2 notches instead, right? In this way, the output, you can see, would have a lower number of values than the input, right? So maybe if I start out with a megapixel image, but I apply a filter that has stride, 10, I'm effectively decreasing the resolution of the image. And I even could have something like this, where if I have a 3x3 filter that doesn't overlap, then I'm actually not looking at adjacent pixels at all, and I could even have situations where I'm skipping whole rows and columns of the image, right? So this is kind of something you'll see as one of the options whenever you implement a CNN is what is the stride, right? One thing to also keep in mind is that no matter what my stride is, that even if I had stride 1, right? Suppose I had a 10,000 by 10,000 image. Well, I'm always going to be kind of effectively reducing the image size because when I apply the filter, I have to make those numbers in the tile match up with numbers in the image, right? And so here I can't go outside the image unless I do what's called zero padding. So, if we want the output to be the same size as the input, we need, what's called padding or zero padding. So that's like saying, suppose I have this image here. I basically am hallucinating that when I place the filter like this, that anything that the filter sees that's outside of the image, we just assume to be 0, right? So this filter would be using some actual values from the image and then a bunch of values that we're just going to assume to be 0, right? So zero padding is also something that if you've done any sort of image processing before, you've probably thought about that just in terms of applying like a Fourier transform or a digital filter to something, right? And then finally, the other thing you're going to see a lot in convolutional neural networks is what's called pooling, right? So in CNNs, we also often see what's called max pooling. Which again is a very simple idea. That's just like saying if I have an output at some layer and I have a bunch of numbers at my output. So here, what I could do is I could split this up into sets of 4x4 or 2x2 images, and I turn this into a result that is twice as small, where each of these guys in this square is basically taking this and taking the max of these 2x2 elements. So this is basically reducing the number of neurons in the next layer by a factor of 4. So this is basically reducing the number of neurons by a factor of 4. So you can either think about this max pooling operation as part of a convolutional layer or a layer that I put on explicitly later on. But if you look at an architecture, you're going to see a lot of these kinds of max pooling operations. Question?
Does it have to be max? Yeah.
It's usually max. Yeah.
Is there a reason for that? Or?
Is there a reason? I guess it's kind of like, a lot of times you're kind of looking to see how much a given neuron responds to something, right? So in some sense, what you're trying to do is trying to take the maximum response, right? There's no reason why you couldn't do just averaging or min pooling or something like that, but most of the time you see max pooling. And I'm no expert, but that's my understanding. Other questions? Okay, so, yes, question.
So this is like after you do the convolutional part and then do the max pooling?
Yeah, typically you do the convolutional part and then you reduce your image size with a max pooling layer. Yeah. And so let me just back up and say, what are we hoping for if we were to have multiple convolutional layers, right? So the hope is that these channels are learning something useful to help us with classification, for example, right? So the hope is that the learned filters at different layers are, are kind of detecting different and useful things. Right? So kind of as a very, super hand-wavy idea, the idea would be, okay, suppose that I have a input image that's of a face, for example, right? And this is some high-res image. And, maybe initially that image also has like, red, green, blue channels. Then I may put that through a sequence of convolutional layers. Or I may put, let me say more precisely, I may put it through a convolutional layer that has many channels, okay? So it's kind of like, first convolutional layer. Well, here, since I'm presumably processing just neighborhoods of pixels, what I might hope is that these convolutional layers are discovering things like I, as an image processor, might think are important, right? Things like lines that are oriented at different orientations, or blobs of different sizes, right? So maybe we could hope for that this guy is detecting, this type of line, and this guy is detecting this type of line, this guy is detecting this type of line. Maybe this guy is detecting like a blob or something like that. So, lines and blobs. Basically like low-level image processing stuff. And now remember that those are the outputs to the next, or those are the inputs to the next layer, right? So now maybe what I say is, okay, I'm going to have another layer composed of more channels. And again, if I suppose that I'm trying to detect, I said faces, but let me back up and say, suppose I'm trying to detect animals or classify animals, okay? So maybe I would say, I could try to make kind of combinations of these inputs that look like facial features, right? So maybe at the next layer, I'm detecting things that kind of look like eyes, and things that kind of look like noses, and things that look like tails, and things that look like ears, right? And then the hope is that at the final layer, maybe I have, a fully connected layer, followed by a, softmax, and that I can make some sort of a animal decision based on combinations of these features, right? Now, this is not something that you can guarantee, right? So like a big problem with neural networks, and one that people are still trying to address, is that they are not interpretable in the same way that humans interpret things, right? You would like it to work this way. You'd like to be able to kind of look at your network and pick out and say, I can see that the network learned how to detect eyes, right? In practice, the network just does what it does, and you have to cope with it, right? And so you can hope that it's learning this kind of thing, but this is just a very hand-wavy notional thing. Question?
So is the idea that kind of like the further you go, the further your layer is into the network, the more specific it's kind of more specific user spaces it's kind of going to look for. It's not specific, kind of like more detailed sense of look for.
I would think of it like kind of going from low level to high level, right? In the sense that at the lowest levels, the network's looking at only a very local neighborhood of pixels, right? Which means it can only learn about very simple, like super tunnel vision information, right? Just orientations of lines and stuff like that. Now, if I go to the next layer, I can imagine that if I've done something like max pooling, reduce the number of neurons coming in, but remember that when I do max pooling, that each of these dots is effectively representing 4 things back at the original resolution, right? So if I do a 3x3 filter on this image, it's actually a 3x3 filter on, it's actually a filter applied to this entire thing. So one way to think about this is that as I go down the network, the effective range of the neurons is much wider, right? So this layer of the network is able to see a lot more than this layer, right? And if I do another layer, then it's even looking wider. That's kind of what I meant by the neuron's receptive field, right? Because as I do operations like max pooling, I am decreasing the image size, but increasing the effective sight of each of the neurons, right? So the hope is that by the time I get to here, the neuron's able to make decisions about dogs and cats rather than just like, orientations of small lines, right? So that's the kind of big picture. Other questions? So typically what you see in a neural network paper or on a GitHub or an archive page is that a CNN paper has usually some sort of an architecture diagram. Right? So it's kind of like saying, usually you kind of represent these like just kind of like boxes that look like this with some abbreviations. So maybe you have like an input image that is usually what you're doing is you're noting the dimensions of each layer, right? So it's like, okay, this is a network that processes RGB 224 by 224 images, right? Then maybe I have a convolutional layer that is 11 by 11 dash 4-96. What does this mean? This is like saying, I'm designing like an 11 by 11 filter. Maybe this number tells me what the stride of that filter is, and this tells me the number of channels. So it's like saying that even though I'm just representing this by a box, I'm actually learning 96 11 by 11, filters, and I'm telling you how I'm applying them with this stride number, right? And then I may have a next layer that says max pool, 3 by 3. And then I may have another convolutional layer that has 5 by 5 filters with a stride of 1, but I'm learning 256 of them or so on, right? ... Then maybe I have a fully connected layer with 4,096 neurons, and another fully connected layer with another 4,096 neurons. And then I have a, this ends with like a, softmax with 1,000 neurons, right? Something like this. This is actually basically, when I talked about that AlexNet paper before, this is actually like the structure of AlexNet from the winning thing. But even here, there's like many more layers inside this. So you basically have this like kind of diagrammatic shorthand for what fundamentally is a very complicated network structure. And so again, typically what happens is that as you go down the network, you have smaller sized filters as you go, but you have more of them, right? That's kind of in practice what people do. And the idea is that these guys here have an effective receptive field that's quite large, right? So if I think about this, this is like saying that these guys can see 11 by 11 pixels. After I max pool it down, then each of these results is effectively like 33 by 33 pixels, right? And then here, if I have a 5 by 5 filter on that, that's like 150 by 150 pixels. So I've suddenly really amped up how much of the original image I'm seeing with that next layer. So that's kind of something to keep in mind. And so, which architecture is best, right? Like, how should I choose the number of layers and the number of channels at each layer and so on? There's no right answer, right? That's the part that makes neural network, training and design frustrating, is that there is no theoretically right answer for how many neurons you need or how many layers you need or how many channels you should have. You just have to kind of, for lack of a better word, keep on screwing around with your network until it produces results that you like, right? And so let me just say that is that, there's no kind of like theoretical right answer to the number of layers, the number of channels, the number of neurons. There are rules of thumb that people, like if you just load up PyTorch and say, give me a network, it will make some reasonable assumptions maybe about things. Although you still, as a user, probably still have to design some of this stuff, right? And so let me just actually show you, an example. So I was working on the homework, and just to show you how easy it is, right? So this is MATLAB. I know that most of you are going to use Python, but it's the same kind of thing where, it doesn't take very much code at all to create a very complicated network, right? So here, for example, this is like saying, the first part is just like loading data, right? And then preparing the data to go into the network. And then this is the critical part that says, what are the layers, right? I have input images that are 28 by 28, because these are like little images, right? Then I have a 64 neuron fully connected layer, and this tells me that my nonlinear function that I'm applying is this ReLU operation, which is kind of like this, hinge-looking thing. And then after that, I have another fully connected layer, and I have a softmax, and I have a classification, right? So this is basically the same kind of thing that I drew in class last time, right? And then I have a bunch of options that say, okay, Atom is the key thing. That's like telling, how do I optimize this? Atom is a fancy way of doing gradient descent with this momentum we talked about last time. And then I have to specify, like, what is my learning rate? How many epochs do I do, right? An epoch is like a pass through the training data. And then there's a bunch of other like little bits and pieces. And then you just say train network, right? So if I just execute this, what you see is, hopefully, this is supposed to pop over to here. Let's go here, right? So what you see is, kind of a, graphical process of showing the network. At the top, you see the accuracy of it on the training data, and the bottom, you see how many epochs, right? This is an older version of MATLAB. Your version may look different than this, so I can see that at the end of this, I got, a training data accuracy that was about like 60%, right? Which is not that bad given that my, this is a 10 class classification problem. So flipping or rolling a 10-sided die would have given me an accuracy of 10%, right? So it's clearly doing a lot better than random chance. And then if I go back to here and I say, well, what about evaluating this on some, testing data? Turns out that the accuracy is only 35% on the testing data, which is, again, not surprising. And there's something called a confusion matrix that I can look at that basically says, what is the true label on the left and what is the predicted label on the right. And again, you're going to be doing this on homework 4. This is basically like a little clothing thing. So you can see that this network has learned how to classify some of these things with super high accuracy, right? Dresses and pullovers and sandals and so on. Here, it turns out that it's classifying like some classes almost entirely wrong, which is accounting for some of the problem, right? So what could I do to fix this? Well, maybe I should go back, and I'm not going to try to fix this right now, but maybe I should go back and I should use more epochs. Maybe I should go back and I should change the network architecture, right? There are lots of things I could try, and that's what the frustrating part of neural networks is kind of like, okay, well, what do I do next to make my network do better? Like, how could I stop it from doing this? And the short answer is, I don't really know. I can't give you great advice. You have to just kind of feel your way through it yourself, right? So kind of what I want to do on homework 4 is to say, okay, actually it's the very same problem as this. I want you to take the same basic idea of one, hidden layer and fool around with this with all the different training parameters so you can get the best you can do with one hidden layer, right? Now, if you want to use the convolutional layer, then I'm not going to do it here, but this is how I would define a more complicated network, right? But now you should be able to understand more or less whatever I said here, right? I've got convolutional layers that tell me, I want 3x3 filters and I want 8 of them. Padding has to do with whether I keep the image the same size. This normalization layer, I didn't talk about that, but that's again just a kind of a heuristic that says after the output of the neurons is generated, I rescale everything before I go on to the next layer. And then I have a nonlinearity, which is the ReLU. I have this max pooling, and then the end, it kind of ends in the same way. Fully connected layer is softmax, right? So it's very easy to generate these networks, and then it's kind of up to you to try and train them, right? One thing I will say, and I'm not sure that this will work on the fly here, so I didn't try it before class, but if I were to go back and train the network, it will take you probably longer to train a CNN than it will take you to train a multi-layer perceptron, right? I'm not going to go through this whole thing, but I can already see that it's doing pretty well, and actually it's doing a lot better, right? So here the training accuracy is already in the mid-80s, right? So by adding these different kinds of convolutional layers, I've already done 20% better on my training data, right? So this is the fun of homework 4 for you to kind of do this yourself. Okay, so questions. I saw a question over there. Sarash?
Wait, yeah. Sorry, I don't remember. It was, so for programming this, are you using a specific are you using PyTorch or something in Python or something, or are you just
Yeah, so what I was using here is MATLAB, but there is PyTorch, and PyTorch looks exactly the same way. So we will provide some pointers for how to do this, but if you can find out immediately how to do this, without more than a single Google to figure out how to do it in Python, because Python is really made for this stuff, right? So let me just say that PyTorch, etc., makes creating and training the networks super easy. Well, in a way, right? Creating is super easy. Training, kind of turning the crank is super easy, but what you can't do, is, except for when it doesn't work, right? So when it doesn't work, as in the network doesn't converge, or it has this kind of thing I showed you earlier where my network seemed to do great on some classes and crap on other classes, that's the part where you just have to keep on screwing around with it until you get it to work, right? And so that's what you're going to explore, I think, on homework 4 is do the best you can with an MLP, do the best you can with the CNN, and then we're going to talk about another method next week that you can try and see what that's like. So kind of these are all different methods of doing classification, and hopefully once you do that homework, you'll have a much better idea for your project about what classification algorithms might be good for what you want to do. So there are a few more things I want to talk about deep learning wise, right? So one thing is that, oh, question. Yeah.
So on one of the CNNs you had written two fully connected layers in a row.
Mm-hmm.
Can you explain that?
It works. the only thing I can explain is that, oh, well, so first of all here, I can explain it here, right? So basically this is a 10 class classification problem, right? So what I'm doing is the inputs are 28 by 28, the hidden layer has 64 neurons, and the output, which is where I'm going to do the classification, always should have the number of neurons that corresponds to the number of classes, right? So there are 10 classes, that's why this is 10, right? And at the end, I take those 10 numbers, I do a softmax to get basically like probability interpretations, and then I take basically the maximum of those numbers to give me the class, right? That's what these last few layers are doing, right?
Yeah, here you only have one, right? But like the one you drew in...
Oh yeah, the one I drew over here, right?
Yeah.
So again, this is an example of this winning architecture from AlexNet. Why are there two of these here and not one or three? It worked, right? That's why. That's the kind of crazy making part is like, why are there two here? That's the part that personally has always driven me crazy about neural networks in general, is that they're just not very explainable, or they're not very, I don't know what's the right word. Like, it's frustrating that there is no right answer other than what seems to work heuristically, right? That's the thing. But we have to get used to it, right? That's just the way it is these days in this modern day and age, right? And so the trend is to, if you can, cram more and more layers into your network, right? So for example, let me just put a couple of notes here. So this AlexNet paper in 2012 had basically 5 convolutional layers, like we were just talking about, plus 3, actually I guess it had 3 fully connected layers, right? By modern standards, that's pretty small, right? That's not a very deep network, right? What came next was there was something called VGGNet. I don't remember the date, but this network had 16 layers, so already twice as many layers. Then there was something called ResNet 50, which had 50 layers, and then there was ResNet 152, which had 152 layers, right? So clearly, the trend is whatever you can cram into your GPU for training, you should try to do, right? And so this, makes it very difficult to understand what's going on at any given point in this sea of layers in your network. One thing that I will say, and this is really important for like, if you're doing any sort of modern machine learning or deep learning, is that I basically have my input, and I have this massive number of layers, this huge black box, right? So if I call this like ResNet 50, and I'll talk about what ResNet means in just a second. This network was trained at the time at some great cost to do the best job it could on image classification, like for example, classifying the classes in ImageNet, right? Now suppose that you as a user say, well, I don't really care about classifying, dogs and cats. I want to classify, I don't know, washing machines, right? I want to classify different kinds of washing machines, and I don't have those in my training data set. So again, how would you do that, right? You're not going to take this architecture and retrain it for washing machines, right? What happens in practice is that you basically cut off the last layer or two of the network, and you freeze everything up to this point, but then you just tune this part for your specific problem, right? And then this is called the backbone. And then the idea of tuning this is called transfer learning. Which is a hugely successful paradigm these days, right? So it's very common to see a paper that says something like, we use the ResNet 50 backbone and tune the last layer, right? That's what that means, right? Is that you take this, tens of thousands of weights that has already been pre-trained for a task that is totally different than the one that you're trying to solve, but then you train the last layers for the task that is specific to yours. And that's much better because since you're only tuning, comparatively few neurons, you don't need to have millions of images of training data anymore, right? You can, if you have a smaller number of training data samples, it makes more sense that you don't have to tune all these parameters. It's kind of like a question about how much data do you need to tune a given size network, right? So empirically, transfer learning works super well, right? And that's what people have been doing for a long time. And again, one nice thing, even though I didn't mention the details, is that even though there are some things that may not be obvious, like max pooling and so on, you can still use backpropagation to train this type of network, right? So everything is still differentiable. I can still push the gradients from the back end all the way through all these layers back to the inputs. And so people are still using basically versions of backpropagation to solve these kinds of problems, right? Now your computer, it may take a lot longer to solve them. Like I'm hoping that the homework problems I'm giving you will fit into your laptop's memory. I think that they should. And like I said, for me as a grad student who grew up before it was possible to train on your computer, it's pretty crazy to see the changes that have been made over just the past 15, 20 years, right? Things that seemed impossible to me as a grad student are now like just taken as normal by you guys, right? So let me say a few words about this ResNet, because that's another thing that is often seen in deep learning, papers and networks, right? So ResNet stands for residual networks. So again, this is a very simple idea, but one that works, again, really well in practice. So the idea is the following. So you can imagine that training a network like this can be numerically super complicated, right? So one thing we talked about last time was the problem of vanishing gradients, right? So if I have some big difference here between output and model, if I have 50 layers to go back through, it may take a long time for that error to propagate back to some of these problem neurons at the beginning of the network, right? So training big networks and getting information to propagate all the way back can be really hard, right? And so the idea is that the observation that researchers made was that while deeper networks can theoretically do more, the performance that you see with the deeper network wasn't always better. So it's not like just adding more layers will solve your problem, right? And one thing that made the training of these larger networks better was what are called skip connections. The idea is that, my normal architecture is I have, some input, I go through some layers. So the observation of a skip connection is that, well, what if I want to learn just like the identity function, right? What if I want X to pass through these layers fundamentally unscathed, right? The problem is that that's very difficult to expect all these numbers to be able to learn that simple transformation, right? What I could do instead was make like a highway that goes from the input to the end of this layers. So it's kind of like, skipping all these layers so that this information is directly accessible to a much deeper layer of the network, right? So instead of going through 10 layers and hoping that this comes through if I need it to, instead I can kind of circumvent this and say, hey, actually, I'm going to pass on the input directly and add it to whatever came out of the layers, right? So these skip connections are a super valuable part of real world networks in the sense that, if this is really important at the lowest level, it's available to the network at later points. Otherwise, if I didn't have this, it may be hard to get that access there. And this simple idea seemed to have a huge impact on the performance, right? So kind of like, to give you some sense, pre-AlexNet performance on that classification task was like 27%. And then AlexNet immediately cut that in half. So that immediately cut down to 15.3% error. And then ResNet cut that down even more to like 3.5% error with 152 layers. And this decrease in error took place over the span of like a couple years, right? Whereas people have been chipping away at this number for like a decade, right? By minuscule percentage points, right? So it was amazing to see just how quickly you could reduce the error on these problems that were thought to be fairly intractable, right? So like it's crazy to imagine that, you know, for example, some data sets are effectively solved by a certain kind of neural network, right? Like the digit recognition challenge of this MNIST, you know, went from being whatever the percentage was, like 70%, to like now it's basically like 99%. Like any modern network, not even with a lot of layers, can do virtually perfect classification on digits, right? So pretty impressive. Another thing that seems to improve practice or performance in practice is something called dropout. So this is, again, a very characteristic deep learning concept. The idea is that, you know, suppose that I learn, you know, a bunch of weights between neurons. So say, for example, I learned these weights were, you know, whatever. You know, dropout basically is a parameter that I set that says at every layer of the network where I apply dropout, just take some fraction of those numbers and set them equal to 0, right? So it's like saying, actually, I'm going to zero out this weight entirely, right? So it's at every stage setting a random percentage or setting a percentage of random weights to 0 at every layer. And again, seems kind of crazy. It's like, why am I throwing away information that I learned, right? Well, it turns out that this has been observed to improve problems with overfitting, right? So this has been shown to improve overfitting. So it's a way of kind of regularizing, right? And actually, you know, you can see here, I'm not going to try to do it right now, but you can see like what happened in this problem that I tried to solve before, right? You know, I overfit, right? So it worked on the testing data. You know, it seemed like it worked really well on the trained data. My trained data, which I guess I didn't record the accuracy, was like in the 60s or 70s, but you know, clearly the testing data was much worse, right? And the algorithm didn't seem to learn that much about what makes a coat, right? Even though it seemed to work okay on my training data. So maybe adding some dropout to my network would have made this better, for example, right? That's just kind of one example of maybe as you observe that your network is overfitting, add some dropout and see what happens, right? That's the kind of recipe that you can do. And then the final thing that I want to talk about, and I'm not going to talk about this too much, but there's something called recurrent neural nets. Or RNNs. So these are specific kinds of networks that are typically used for processing what I would call like time series data, right? Things like, you know, speech or audio or music, where the samples are basically relayed to each other in a temporal way, right? So these are used for processing time series data. Like, you know, music, speech, audio of any kind, right? And so the idea here is that, you know, suppose I have like a kind of a layer here. Just draw a fully connected layer. So the idea is that what I do is, in addition, and I imagine that what I'm doing is I'm presenting the network with a sample at every point in time, right? So what I could do also is I could take the output of each of these nodes here, delay it by one time step, and I could feed those back into these neurons as additional inputs. So the diagram gets a little more complicated, right? But if you're a signal processing person, like if you've taken a DSP class, you recognize this is what's called an IIR filter, right? Infinite impulse response. This is basically like, related to what are called IIR filters, or also what are called autoregressive processes. We're not going to talk about this in any more than what I just said here, but just something that you may see in a paper, right? Especially if you're operating on something that is like a time series. And you can also kind of what's called unroll this network in such a way that it just looks like a bigger neural network like the type we already saw. It's just a lot messier to draw as opposed to putting this little delay block in here. So again, probably not anything that you guys have to worry about other than if you happen to be doing a project, for example, that involves processing data that is like the same sample of an object over time, well, maybe you might look at what is the recurrent neural network and will it help to solve your problem, right? Just as a side note. And then finally, there's a network structure called attention. You may have heard of transformers, right? We're going to talk about that a little bit in the context of this generative AI lecture that I'll give in a few weeks, right? So there's a specific kind of network architecture called a transformer that apparently now is like solving all the problems that, that can be solved. And so we'll talk a little bit what that means. It really isn't anything more than a complicated, series of network connection blocks. It's just a different kind of architecture, right? So that is the crash course in deep learning, right? So if this is all interesting to you, then you could take the deep learning course, I believe, next semester. Is it next semester? Yes. So this is like the whirlwind tour of what you might see in a deep learning class, right? And of course, you'll be doing all this stuff in deep learning homeworks and so on. The furthest I'm going to go for this class is ask you to implement, in the PyTorch kind of simple world, an MLP and a CNN, and kind of keep on trying to tweak the parameters of those things to get good performance. And I just want you to kind of get a sense for, okay, this is what neural network training is like in the modern day and age, right? And then we'll see what performance people can get. Okay, questions or comments? Okay, so let me pause or stop the recording.